we doubled our expectations in the recorded data volume. And this gives us a tremendous sensitivity for physics at the new energy. Remember, in 2015 was the first run at 13 tera electron volts. This is a measure for the energy in the collision of the two protons. And we recorded a small amount of data. In 2016, this year, we basically went to routine running. And with that amount of data, we are now ready to push the energy frontier for new physics if it chooses to emerge at the high masses, at the high energy. So what the experiments have done this year, reported in the summer conferences or already with an intermediate result, is increase the sensitivity for searches. And some spectacular results have come out and have been shown. So remember, 4 years ago we discovered the Higgs particle at CERN. The Higgs particle is a very peculiar object because it's the only one particle that couples to the mass and only to the mass of particles. And with this coupling, we can predict the branching ratios of the Higgs decay. Branching ratio, it's a random process. The Higgs basically chooses whether it decays into B mesons, couples to top quark pairs, and all this is happening in a random fashion, and some of these decays are very rare. We have precise predictions from the standard model for these decays, and we now are measuring this. So these years of run 2 are the precision physics with Higgs. And what we really hope that it is not only standard model physics, but the really new physics is hiding behind some of these decays. So suppose one of the branching ratios is suddenly twice as large as expected. And this is almost certain new physics that is hiding there. Dark matter is an enigma in the whole search since several years. We know that currently we understand 5% of the energy density of the universe. A lot of that is dark matter, in other words, mass that doesn't couple to the known particles that we have today. Whether this dark matter particle chooses to couple to the Higgs in a special way is another question. But the experiments are more universal than just looking into the Higgs decays. They have specific dark matter searches. And one of them is through a heavy boson, extra boson, and other variants which they analyze in their data. So the short message is there's a wealth of data, and the experimentalists are really going through this amount of data and trying to understand it from all ways of interpreting it. No, I don't, because research is not about predictions. This is not a technical enterprise. We understand we need much more data, but what will happen with more data is you increase the statistical significance and sensitivity. If I were to predict when it happens, I would have the theory that explains everything. And if I would have the theory, it would probably make other predictions, and you would immediately tell me, oh, this is in contradiction to an observation out here with the stars or something like that. So, no, there is no shortcut there. Exactly. I mean, all of this could happen, that you have a mass density that exists for a short while and then disintegrates again, which would be called a black hole. It's not like the black holes that we see out there, or that was creating so much news earlier this year when two black holes merged. It would be completely different, but yes, this could happen. So in general terms, what we're trying to do is experimentally exclude all these interpretations for which theorists have given us so many explanations, and verify them or falsify. And of course, it would be nice to discover something, but as I said, this is not predictable. And somehow the most urgent is the solution to dark matter, because it's such a burning question. It's so dissatisfying that we know there is mass out there and we don't know how it is made of. So I think this would be this is simply a needed discovery, and where it will happen, I don't know. I should be very modest here in this. At this moment, LHC is one area where one looks for dark matter particles. There are underground experiments, so in a very quiet environment where one searches for dark matter as well. So as an experimentalist, we simply feel the obligation to look everywhere. Okay, and then of course the nicest result is an unforeseen discovery. So you go systematically through the data and then suddenly you see something that shouldn't be there. And if you look back, this is how many building blocks of the standard model came about. The charm quark, for example, was discovered almost inadvertently. Initially, people thought the cross-section measurement didn't work, so the counting rates wouldn't fit. So I think we have two avenues there. One is using a larger circular machine. This is the Future Circular Collider, a study which we have undertaken or are undertaking to explore whether it is feasible at all to go to a 100-kilometer ring. This is really not small. To 100 TeV, so basically 7 times the energy we have currently, and then explore that, or whether it is a linear collider in which we would collide electrons with electrons and use elementary particles to produce a final state that maybe exhibit new physics. Both of them are explored. We will try to see what is feasible, what is most attractive and promises from the theoretical understanding, but also from the LHC data. And now I should caution you, the LHC, we have a program that goes till 2035, 20 years more. So a little bit of patience is required. We have something like 1% of the data accumulated. But you're completely right to see whether a new machine is feasible. One has to start now. The construction time would be something like 10 years. So it's all in time, and in due time we will be able to take an informed decision. Let's put it that way. I think because it really touches the fundamental questions. When you are growing up and wonder what to do in life, you are really intrigued by the fascination of fundamental questions. How did we come about? And on the other, so this is the one motivation. The other one, there is already a lot of simplicity in our standing of the emergence of the world, of the universe. As I just explained, a few building blocks are still missing, but it's fairly concise. And I think this is such a motivation for young scientists to engage in that and be the discovery who finds that missing building block. And then what happens is typically these people engage in experiment and then they have a family to feed, and then, okay, they sometimes think, well, maybe I should go and get a living somewhere else, which is fine because the education they get in this science environment is really helping them a lot to find a job everywhere. Or they choose to be researchers and they stay in the field at the university or at CERN or other research center. But I think the motivation is really the fundamental question. You don't study physics because you want to invent the next refrigerator or something like that. it's very short-sighted not to spend it. So I'm not trying to be a spendthrift. First of all, I think we try to be still very economical in the way we go about particle physics. So we have only one center in the world. We invite scientists, the best scientists of the world, to take part in these experiments. And then if you count per scientist, it's actually fairly reasonably priced. I'm not trying to belittle the big numbers and the budget that is involved, but just to put it into perspective with other science projects that elsewhere are done. So the other part is, should we do this? Is this something that society needs? I think yes, absolutely, because when we speak of innovation, we are looking at the process in which we have an idea and we take it to the market. But what if you run out of ideas, real ideas? The inspiration comes from asking these fundamental questions. Like when Hertz detected the waves that now drive or fuel our mobile phones, he clearly didn't think about communication. It took 100 years till we had the mobile phones, but now we use them every moment. I'm not saying that this will happen to quarks eventually, but it's this long-range thinking that you have to have. And so what we see in growing societies that are developing on the technology frontier is they very quickly also branch off into fundamental science. Not necessarily particle physics, it can be astroparticle physics, it can be cosmology, but they realize that training young people in this very fundamental branch is helping them in the end, because it broadens the perspective and then feeds back to society. So I think it's absolutely needed and would be short-sighted to cut.